moving here. And I know you couldn't anyway, but when I checked with Miss DeRacy, I mentioned that I said, she said, no, you've got an associate degree, so you can't do math. But you can. Right. But I understand. All right. We are recording, and I did want to, and I can't remember if I tried to use this on y'all last time. I probably did. How much, I just realized PowerPoint opened 2 or 3 times, but it's still okay. All right, but I think I told y'all this time before, the PE exam, doing something like math team would really help you. The PE exam is in many parts. That's professional engineering exam. And there's one part that used to be called the EIT, Engineering and Training, that you took a test for. I think they call it something else now, but there's always a math section. And the math team, the skills you get in math team are the very ones that would do you in great stead when you're taking those exams. Help you do the problems faster, you know, come to them. But I know y'all can't do them. So anyway, we'll get off of that. All right, your text has what? Okay. It's the same caption on both of these. Magnetic resonance imaging of veins in a patient's heart. The MRI scanners use mathematics and Fourier transforms to construct 2- and 3-dimensional images. They show the device here and someone looking back at the monitor, which is showing what the device is seeing. In the new text, they actually show a picture, an image that was done by MRI, which is pretty cool, but you think, so what? I mean, we aren't going to get as far in this chapter as doing anything quite this complicated, certainly not Fourier transforms or anything else, but it just shows some of the stuff that math can do. All right. Now, what we're doing now, we talked about that integration is basically one way to look at an area under a curve. If you're integrating a function, the curve of that function, the integral represents the area under that curve. Because if you think about it, it's if the curve's greater than 0, you know, above the x-axis, then that's the height of a little segment, a little strip of width dx. That's the height is the value of the function. Dx is the thing. Integrating that is basically summing it from here to there. That gives you the area under the curve. That's what integration does. Well, not just will it give you the area under a curve, it'll give you the area between 2 curves. And I don't know if you were aware back in 2009 and 10, I don't know, y'all were probably infants then, you know, but so young, I don't know if you remember, that was the big recession. It just got started around 2008 or a little before that. And they had this program they had trying to stimulate ourselves out of that recession, and that was called the government stimulus spending. And this was a graph that you were seeing then. They were using part of the stimulus dollars to try to improve the renewable energy capacity, and companies were given all sorts of things. This was the expected growth. The blue curve here was the expected growth from the standard traditional production of energy, and this was the projected growth if they use this stimulus spending to come up with new capacity with green energy, how much more it would be. So you're not interested in how much it would be, but how much it would be increased. That would then be the difference between 2 curves, okay? And this, again, you can do this. What you do now is the area under the red curve minus the area under the blue curve gives you the area under P there. And that's exactly what you do here, is integrate from, and you wouldn't usually use 2010, you'd probably do 10 to 30, just to keep from having such huge numbers in there. You could actually do 1 to 3 and let those numbers represent 10 years, but 10 to 30 probably would make more sense, and integrate the difference between the two curves. Then that's another application of an integral, okay? So said in math speak, not just looking at a graph, but if you're the area between two curves, between the graph of two curves, now the understanding here, alpha and g are both positive functions, okay? So you don't have anything below the x-axis. So x-axis down here, alpha's up here, g's up here, okay? And sort of the understanding is alpha is greater than g. It doesn't have to be, but most of the time we're going to say it's greater than or equal to g everywhere between a and b. Then the area between the graphs would be the area under f minus the area under g, and that would give you the area in between, just like we saw before. And the other way to say that, the difference of two integrals is the integral of the difference, if the limits are the same and both of these are integral functions, okay? And sure enough, that's a kind of like a linearity rule for integration. They don't call it that, I don't believe. Now, what they were saying, and I sort of skipped over this, I said all these words, but I didn't give you the term for it. Suppose we are given two functions, f and g, okay, such that f of x is always greater than or equal to g of x, okay, on some interval a to b. We call that region vertically simple. That doesn't mean simple-minded, no, it means that you don't have any place where alpha then dips below g, and therefore you would have to stop and split it into different pieces. This is vertically simple. Alpha is always greater than or equal to g, okay? Vertically simple, okay? Now, I don't see figure 2 in your text on this slide set. So let me just make sure it doesn't show up next. It doesn't. So let's take a look at it first. Okay. Oh, you both of you have it. Okay. So I don't have to hold it up there. The figure 2 shows the function coming in, and f and g cross at a certain point. That's at x equal a. But then from there on, f is greater than g. Anywhere less than a, g is greater than f. If you included anything before a, that would not be vertically simple. But from a on, at least as far as they show here, a to b, that's vertically simple. The vertical lines, the upper graph part of that would be f, the lower part g. Even though at a, they're exactly the same, well, that's where they're equal, that's fine. But except for that, alpha is always greater than that. All right, then getting to this graph, let's see if I can get all this on one graph. Okay, here's the region between graphs A and B, between x equal A to x equal B, f of x, g of x, f of x always greater than g of x, so that's vertically simple. The area between those two is given here, be the integral of f of x minus g of x. Okay? Now, that's what I just said is here. Area under f of x is this whole area here, the light tan and the dark tan, or whatever you want to call that. That's the area under f. The area under g is the dark tan part. So if you subtract this from here, that goes away, and you're just left with light tan. And that, sure enough, is the area between the two. So that makes sense. Graphically, it makes sense. Analytically, and with, as well. Okay. think this may be the figure for example 1. So let's do example 1. Find the area of the region between the graphs of the functions f of x. Let me get my pen activated here. The system is really, really slow. There we go. Got it. Okay. F of x, well, here it is. Here's f of x. Okay. And here's g of x. Okay. And we're going from 1 to 3, as shown in the figure here. It says find the area between the graphs of these two functions. Now, guess what? On a test, you would just be given that without the figure. Find the area between the two. So basically, what you have to do is sketch your graphs yourself, okay? To make sure that f always stays greater than g. Now, I was going to say to make sure which one's on top. Really doesn't matter if when you did the integral and you came up with a negative answer, you knew you just had them reversed, okay? But not a bad idea to sketch first. Now, if you have a graphing calculator, sometimes you can get that to do the sketching for you, and you see, yeah, they don't cross anywhere, and f is always on top. Yeah, so we'll go with that. So I'm not going to do the second part. I mean, they've already drawn it for you, so let's move on from there. And let's do the integral. Find the area between those two curves. Okay? Well, there we go. Pen not wanting to come up. The area between the two curves would then be, as you see here, f of x. Where is my graph? Okay. All right, sorry. Area between the two curves would be f minus g, so that would be, let's go on and just write it this way. X squared, and it's going from 1 to 3 because that's what x is going between 1 and 3. Your dx determines what you put there. X squared minus 4x plus 10 minus, now, after a while, you may not have to, but at least to start with, I would suggest putting this in parentheses. 4x minus x squared. Then do your dx. Okay, there's your f minus g. Now, you can put f in parentheses too if that helps you see it better, but that's what you're integrating. Because you know f's on top, g's on bottom, so f minus g should give you a positive area. All right. Now, the reason I suggest that you do this is to keep from making a sign error. And those are so easy to make. 1 to 3, I'll do it in gory detail. X squared minus 4x plus 10 minus 4x plus x squared. See that? Distributing the minus sign across the parentheses. And that's all times dx, and then combining like terms, it's integral from 1 to 3. You got x squared plus x squared is 2x squared, minus 4x is minus 8x plus 10 dx, right? Can you do that integration? Antiderivative of 2x squared. Say again? Antiderivative. You're integrating. That's antiderivative, right? Okay. All right. Okay. Well, let's just write down the 2. In fact, time out. I hadn't even noticed it. Now I noticed it. Notice each of these has a factor of 2, doesn't it? So let's get that out of there. 2 times the integral from 1 to 3 of, what would that be? X squared minus 4x plus 5 dx. You don't have to do that, but it just keeps the numbers simpler. 2, now let's do antiderivative of x cubed. X cubed over 3. Now, the reason I stopped and did this is if you'd have left the 2 in there and then the antiderivative of that, you should get the same thing. And notice what that would be. 2x cubed over 3. You somehow pulled the 3 out there and multiplied it by 2. That's divided by. So that's why I said, okay, let's back up, factor that out. Okay. All right, next term. Minus, good. All right, bonus points, okay. 2x squared. And always, if you want to check and see if you did it right, just take a derivative. Derivative of this is x squared. Derivative of this would be 4x. Yeah. Okay, minus 4x. Okay, next. Plus 5x. Okay, and evaluate that from 1 to 3. This is actually the hardest part of the problem, okay? You got a 2 times. So let's plug and chug, and what do we get? Say again? Nine. Okay, yeah. Plug in a 3. 3 cubed is 27. Divided by 3 is 9. Okay. Next. Minus, what'd you say? 12. How'd you get that? Okay, 3. Okay. To 18. Minus 18. All right. All right. Let's go back to our, never mind. Okay. Next. Plus 15. Now what? Minus, now again, not a bad idea to do this in parentheses. Let me put a parenthesis rather than a bracket, because we already got a bracket in there. Okay, let's plug in the 1 there. What do you get? 1/3 minus 2 plus 5. Okay, in parentheses there. Okay, so let's see what we got here. 2 times. All right. Let's combine like terms and what do you have there? Six. Okay. Another way would be 24 minus 18 is 6. Either way you want to do it. Okay. Minus now. This is sort of a pain in the neck. Let's do the whole number part first. What would that be? 3, okay. It may have been a week since we've been here, okay. And then we can go and add a third to it, 3 1/3. Is that all right with y'all? Do it that way? Okay. Because it's plus 3 plus 1/3, but there you're subtracting that. All right. Now, there's a couple ways you can go here. I'm going to do it one way, which probably isn't the best way, but it's how I like to think of it. That would be 5 3/3. Isn't that 6? Okay, minus 3 1/3. And that would be what? 2 2/3. So you got 2 times 2 2/3. Okay. Now you can either do that in your head or change that 2 2/3 to improper And that would be 2 times, that's probably the easiest way. Wouldn't that be 8/3? Okay. I don't know where my pen's gone. Okay. Why did it do that? That was totally bizarre. It just decided to shut down.